Swayam Prabha. Digital India. Educated India.
Today we are going to start discussion on the eutectic alloys in detailed manner, because eutectic is very important system as a part of the solid liquid to solid phase transformation. And last part of the last lecture I have shown you a eutectic phase diagram and discuss about some important features. Now today I am going to begin with showing you some morphologies of different eutectic types. These pictures are taken from one of my colleagues' book, former colleague Professor S.P. Gupta at IIT Kanpur, in a book called Phase Equilibrium Materials. The eutectic, because it is a multi-phase, specifically in the binary eutectic is a two-phase mixture, so therefore there are different morphologies possible. The most commonly observed one morphology is the lamellar. As you see here, that the black and white lamellae of the two phases are seen in these microstructures, and sometimes they will be broken, sometimes the broken lamellar, or sometimes they will be continuous, but they are actually in 3D slabs of two different phases arranged in a particular fashion. In some cases, this lamellar morphology can also form cells. The cells which we have discussed for the dendritic growth, same kind of cells can also form here. And you can see here that this is a boundary or the front between solid and liquid boundary of a cell much earlier. Now it has grown up bigger or larger portions. So here again also the morphology is lamellar, but it forms like a shell between two eutectic. Also one can have a rod morphology shown here. Rod is basically that one of the phase is, instead of a lamella it becomes rod, other phase remains continuous. Lamellar morphology is seen widely in lead tin, bismuth, antimony, many other systems. On the other hand, rod is not observed so frequently. It is seen either in nickel aluminum or niobium silicon type systems. Rod morphology is normally observed in the eutectic system where the rod phase volume fraction is relatively lower. As you see in the lamellar morphology, the volume fraction of the two phases is almost similar, but when one of the phase is volume fraction is low, then the rod type of morphology is observed. One can also have very peculiar morphology like spiral one shown in this picture. You see here the one of the phase has formed like a spiral staircase. If you observe a staircase which is like a spiral, it looks like exactly same. Many cases it looks like even dislocation multiplication also. This one spiral eutectic normally forms in magnesium zinc system, and it has been found that if the thermal expansion coefficients of one of the phase is distinctly different from the other, then this behaves like a two plates sitting on each other like this, and then if you heat it up or high temperature, one of the phase expand more, and then they try to compare to the other and try to bend, and in the process finally it forms a spiral. So this is observed in a magnesium zinc system. Aluminum silicon, which I discussed in the last class, also a very classical system, because these eutectic alloys are used in the real industry like cylinder blocks in many of the cars car engines, and the eutectic morphology is known as acicular. The continuous white phase is aluminum solution, and these long fiber like features you see here, black color, is basically pure silicon fibers. Normally this eutectic is very hard and brittle, but these can be modified using very small amount of sodium, strontium or some other mixture of mixed metal, and the morphology of eutectic can be modified, which we will discuss probably in next lecture. And this is a typical feature of silicon. Silicon actually is a metalloid, so it grows like a fiber. Now, another very common eutectic is cast iron. Cast iron has different type of morphologies, eutectic cast iron, because cast iron is an eutectic alloy between iron and carbon, and by addition of magnesium can modify the morphology of graphite, which is shown here as like a black blobs or spherical spheroids rather, and the matrix here is basically almost pure iron, alpha iron. It can also be pyrolytic type, but important aspect is that eutectic reaction was happened and high temperature and lead to formation of these globular or nodular the graphite in a gamma iron matrix. One can also have a very distinct morphology known as Chinese script, and this is seen in bismuth cadmium system. And if you clearly see that eutectic looks like a typical Chinese characters, and that is why it is known as a Chinese script morphology. This is again a field of intense research, because this different morphology of eutectic is mainly because of many aspects. So, that cannot be discussed in a lecture like this, because that is a separate aspects, but fact that these different eutectic systems from different morphologies makes these alloys very interesting. Remember one thing, eutectic is a reaction from a liquid forming two solids. So, therefore, two solids forms in a binary system simultaneously, cooperatively from the liquid. So, now in order to understand how this eutectic really forms or how the eutectic really grows, we will show you how it actually happens. So, let us go to the board and I draw a simple phase diagram and explain you how the eutectic, what is the mechanism of formation of the eutectic. So, if I take a simple phase diagram which is shown you in the last lecture, with two terminal solutions, one alpha, other one beta, with a eutectic point at XBE, temperature TE, this is typical phase diagram. Now, we are going to discuss solidification of the alloy whose composition is exactly XB. So, as you know, the liquid transformed to two phases alpha and beta simultaneously once it is cooled down to temperature below TE. So, what actually happened? Let us suppose I have a liquid with a composition equal to XPE. Now, nucleation can happen any of these two phases, either alpha or beta. There is every possibility that both can nucleate simultaneously or both can nucleate separately. Let us suppose alpha is nucleated. This is alpha nucleation. Okay. This I write down, this color is alpha and this color is beta. Okay. So, once the alpha nucleates, what happens? See, alpha is basically a rich phase. If you look at it, the composition of alpha is basically at the eutectic temperature is this, which is close to A. On the other hand, composition of beta is close to B. So, that means it is a B rich phase. So, once but liquid has a uniform composition of XPE. So, as soon as the alpha nucleates from the liquid and it start growing, alpha requires more A. So, therefore, it will remove all the B when it grows. So, as the alpha grows like this, suppose alpha is growing like that, alpha, let us draw it from the boundary, that is better. Alpha grows, it rejects all B, okay. So all B will be rejected here in front of that, all B will be rejected. So all the liquid has a compositions of XBE, because growth of alpha requires more A, less B. So these nearby regions will be rich in B, very rich in B. Because of that, the composition of the liquid might reach the point corresponding to these, okay, the point here which I marked XB beta. So as soon as it will happen, there will be finite diving force available for the beta to nucleate and grow on the both side of alpha. That is because you have sufficient B available in the region near to the alpha, side by alpha or in front of alpha also, but it is always better to nucleate on the top of alpha, right, that is always better. So now I have two beta lamella or beta phase, two lamella or beta phase, two lamellae on the both side of alpha. So if these two beta phases has to grow, they will also reject A, because beta is basically rich in B, sorry. So because of that it will reject all B, sorry, it will reject all A, yes, right, A will be rejected as the beta grows, beta is yellow color. So because A is rejected now, again the liquid nearby beta will be rich in A, because beta requires more B, so less A, so A will be rejected, and because of that again the composition in the regions nearby beta will become very rich in A, and finally it will reach XB alpha, and again alpha will nucleate. And because it is now the nucleation is very easy, because you already have a assemblage of alpha and beta. So obviously alpha will nucleate on the sides of the beta, and again as the alpha grows it will reject A, sorry, it will reject B, and again nearby regions will become rich in B, and then beta will nucleate. So that is how actually the lamella eutectic grows. So if I have to draw a complete full eutectic with the lamellae of alpha and beta, it will look like this. This is my alpha, this is my beta, another beta on this side, then another alpha, and so on. So finally you form a colony like this with alpha beta lamellae. Like that, and that happens in everywhere in the liquid. So it can also happen here, it can also happen there, it can also happen here, it can also happen there. So finally the whole sample will become full of eutectic. That is what actually seen in these microstructures. Now the things will be little bit different when you go from lamellar to rod or to even nodular or acicular eutectic, but mechanism will remain same. Mechanism is not going to vary, because in all these eutectic phase diagrams one phase will be rich in A, other phase will be rich in B. So it does not matter whether you are forming a morphology like lamellar or rod, the rejection of the solute in the liquid and the side regions will be very important. The important lesson which you observe here as compared to a dendrite. So when a dendrite grows into liquid, what happens? As the dendrite grows, it also rejects solutes, alloy dendrites, right? And it rejects solutes in all directions, because as the dendrite goes a solid phase, the solid has a much lower solute content than the liquid, and it goes from the liquid, right? So because of that, the solute which is excess is rejected to the liquid, and for further growth of dendrites these solutes needs to be taken are transported further. Okay, that means this solute needs to be moved away from these portions of the dendrites, and this kind of diffusion is a long distance. This requires atoms needs to move a quite long distance. So that is why dendritic growth is mostly governed by the diffusional flux of the solutes from the tip of the dendrites to a larger distance. But on the other hand, in eutectic, if I draw it again, this lamellae, only 2 lamellae, 1 alpha and 2 beta, I will be able to explain you nicely. So alpha will reject A, B, okay. This B is required by beta, right. As the alpha rejects B for its growth, this B will be required by the beta for to grow. That is obvious, because the beta is rich in B. So this B can then get transported from the tip of alpha sidewise. It does not require to be transported along this direction, it can be always transported sidewise. So diffusional distance from the alpha to beta is very small, because these 2 lamellae are sitting side by side. In fact, in eutectic growth we always define interlamellar spacing called lambda. So diffusional distance is related to lambda. It is actually either equal to lambda or a fraction of lambda. Similarly, as the beta grows, it rejects A. This A can again transported to the nearby alpha. So therefore, the growth of alpha and beta are coupled or cooperative. As the alpha grows, it rejects B. This B is used to feed the growth of beta, or this B is required to growth of beta. Similarly, as the beta grows, it rejects A. This B, A is required for the alpha to grow. So this is like a cooperative phenomena. They both are dependent on each other. The growth of alpha is interlinked with the growth of beta. They cannot grow separately, it is impossible. And because they cannot grow separately, that is why it is called a coupled or cooperative growth in eutectic normally. So this is distinctly different from the dendrites. Dendritic growth does not require such a kind of coupling of the diffusion fields. Remember, the atoms from the tip of alpha, basically B atoms, they have to diffuse sidewise to reach the beta lamellae. Similarly, A atoms rejected by beta have to diffuse sidewise to reach alpha. These arrows indicates that, and this is completely interlinked. So therefore, this growth of eutectic is basically diffusional in nature, and any kind of a model or mechanism for the growth of the eutectic must consider how this atomic transport happens across the interface sidewise. So finally, when the eutectic grows, it never have a flat interface, it has a curved interface. I drawn that picture, right. The first question one always asks, why can't we have a flat interface like this instead of interface like that, okay, the way I have drawn, and this is the one we see in the actual case. This is mainly because alpha and beta has different melting temperatures. You see here, alpha has a melting temperature of this much, beta has a melting temperature of this much. They have different melting temperatures. This has a melting temperature given by this point, this has a melting temperature given by this point. So now question is that, yes, they have different melting temperatures, and obviously they may have different crystal structure also. Even if they do not have or they have, does not matter, they have different melting temperatures. But because alpha and beta are growing side by side, they are in touch with each other. So therefore, the temperature must be continuous. Temperature must be continuous from beta to alpha, alpha to beta. You cannot develop a temperature gradient across the interface. This interface between alpha and beta must have same temperature. So in order to make the temperature same, these lamella are actually curved, so that the curvature and undercooling, the undercooling because of curvature are tuned to make the lamellae curved. So therefore, depending on the, that is one aspect, depending on the melting temperatures of these two phases which are growing side by side, the curvature can be changed. Okay. Second important thing is that, you know, at the interface, if I draw again other way, vertical way, bigger, at the contact point here, if I draw the interfacial energies the way we have shown you earlier in case of, so this is interfacial energy of alpha beta. Remember, we have liquid in front of which, so therefore this is interfacial energy of, this is your alpha, central one, these two are beta. So therefore this is interfacial energy of beta liquid, this is interfacial energy of alpha liquid. And if this angle which is subtended by these two, so therefore at this point these three interfacial energies must be balanced. So it is very simple that if I draw a normal vertical like this, so as you clearly see the angle will be subdivided by theta by pi by 2 pi by 2. So I can write down gamma alpha beta must be equal to gamma beta L, okay, this is gamma beta L plus gamma alpha L cos pi by 2. Okay, the addition of these two, you know, terms in the vertical direction must balance this. Similarly, gamma beta L sin theta by sin pi by 2 must be equal to gamma alpha L sin pi by 2. These two are actually horizontal components. So finally, balance of these interfacial energies as well as the curvature under cooling determines the actual shape of that, actual shape of the interface. That is very important, because these shapes of the interface tells you what is the interfacial area. And remember, the interfacial area multiplied the interfacial energy, that is what governs the driving force per solidification. Anyway, this is basically happens in a eutectic, lamellar eutectic growth. Things are a little bit different, or not a little bit, quite a bit different in case of rod or in case of other eutectics, because the complex microstructure is, the type of complexity is more. But for your purpose, it is always more than enough to understand how a lamellar eutectic grows in the liquid. So this is actually the mechanism of growth of eutectic. Now question is that whether can we build a mathematical model around it or not. To do that, let me just I just discussed with you. So as you can understand, two important aspects which play a role in the eutectic growth. One, the transport of these atoms from the tip of these lamellae to the other, right. So one of the lamellae alpha is rejecting B atoms, that needs to be transported to the beta and vice versa, that is beta lamellae rejecting A needs to be transported to alpha. That means this is a diffusional process. So because if these atoms are not able to diffuse easily, the growth of this front, eutectic front, the liquid will be slowed down. So growth rate will be distinctly dependent on how fast these atoms are transported or diffused rather, or transported via diffusion across this interface, not perpendicular to the interface, across the interface, remember this way, parallel to the interface rather, okay. So therefore we need to calculate what is the undercooling required to diffuse or transport these atoms. That is the first part. That is very important, because this is will basically govern, or rather will basically dictate how fast this eutectic lamella or eutectic colony can grow into the liquid. Second important aspect just now I discussed is the undercooling required for the curvature. So that means what? The total undercooling required for the eutectic growth is basically equal to undercooling because of the curvature, that is I have given R, okay, we always write R because these are curved. So there is a radius of curvature and the compositional aspects delta Tc. These two needs to be calculated separately, then only we can develop a model. Now this, once I know this delta T, then I know what is the driving force delta G available, right. So therefore if I write down here delta G is basically because of this delta T, that can be easily written like delta H delta T by Te, right. That we have already seen how to calculate that. Delta H is what is the latent heat of evolution because of the eutectic formation, and delta T is the total undercooling. If this is the total undercooling, this is total undercooling divided by the eutectic temperature is what is the driving force available. Now this driving force available is spent in two things. One, for the interface to grow, for these whole things to move into the liquid faster. Okay, if this is liquid, this whole thing will grow into the liquid. Second thing is to create an alpha beta interface, because there are two things here. One is the interface between alpha and beta, other one is the interface between the lamellae and the liquid. So I just need to add the energy required for that. So this is minus, as you know, correct. So if I write down this as a G when the interlaminar spacing is equal to lambda, G is equal to minus delta H delta T by Te plus the energy because of interfacial energy, okay. That we always write down A gamma, right. So what is A here? Remember A is basically proportional to lambda. Basically A is proportional to twice by lambda square. So normally people write this is equal to 2 Vm by lambda alpha beta, where Vm is the molar volume of average molar volume of alpha and beta, okay. So the actually the surface area of 1 meter cube of eutectic is equal to 2 by lambda square. That is what is the calculation shows. So now this is the delta G or the free energy for the transformation of the eutectic with interlaminar spacing equal to delta. Question is this: at when the total energy which has been obtained because of the latent heat evolution or because of that is equal and balanced by the formation of the interface, then I can write down this to be equal to 0. That means there is no finite driving force available. So this will give me a delta star, the minimum value of lambda star, minimum value of lambda, and that is equal to basically twice Vm and gamma alpha beta, the surface energy Te divided by delta H into delta T. Is very simple, you just simply back calculate, it will get it. This is the minimum value of lambda, you cannot have less than that, because as you know, as the lambda goes on decreasing, surface area increases. So therefore this part, because lambda is at the denominator, so because of it is increase of lambda, sorry, decrease of lambda, that means when the lambda becomes smaller and smaller, this part will increase, the value will increase. So therefore this is basically minimum value of lambda. Now it is very simple actually mathematically. So that means the whole energy which was available to the system has been spent on creating the interface between alpha and beta. That will never happen in the actual sense, because in that case eutectic has no energy available for it to grow. So lambda will be always higher than lambda star. That is very simple. Okay, so we will stop here. In the next lecture we will discuss how actually I can use total undercooling terms to formulate a theory to calculate what is the lambda, what is the velocity of the interface, how they are related. Just like in dendritic growth, the velocity of the dendrite as well as the the tip radius are related by a single equation. So, we will also see that this is possible to develop such equation. In fact, this theory was formally developed by K. A. Jackson and J. D. Hunt in 1966, and classically this theory is known as Jackson and Hunt theory. So, those of you who are really interested to know how this theory was developed by Jackson and Hunt, this paper was published in Transaction of American Metallurgical Institute of Engineers, something like that, AIME, Transaction of AIME, American Institute of Metallurgical Engineers. This was published in 1966, where the detailed description of how this model was developed is provided. So, in the next lecture we will start with that and describe, although it is not possible for me to describe the whole model, but basic features of the model will be discussed, so that you understand how the eutectic actually, laminar eutectic actually grows into the liquid. So, we will stop today.